Start with the generative classification. What we want to do is that we want to first to model the general form of this classification, and then go over the special traits. So we know in generative classification the probability of class basically given the specific class. Probability of class K given X comes from the prior of X, the likelihood of X times the prior of K, right? And we know for the prior is simple, you can just look at your data and then calculate the prior. So let's say we have a data set which is x1 all the way to xn, yn. Okay. So we know these points are IID. Okay. If they're IID, that means the probability of data set, which is the same as probability of y1 to yn, given x1 to xn, right? This comes from the multiplication of probability of yi given xi. So now this formula that we wrote is for a given class, right? That means that you are looking for a specific class, but that equation that we have here is probability of yi. So it doesn't say which class, right? So that means that we need to write that formula somehow. That doesn't matter which class you're looking for. It gives you the answer that you want, right? So we know that this is equal to probability of xi given yi times probability of the prior of yi, correct? Because this is a generative one. Now let's go here. Probability of yi, okay? Yi. You could have any out of like k classes, right? That means that you could have k priors. So we're going to show the prior with the theta y, and then here we're going to put k. K stands for the class, y stands for the actual variable that you are looking for, which is this is the prior of y in class k. Okay, so the next one is the likelihood term. Now, in order to understand the likelihood term, let's assume you have the following data set. I'm just right now assuming y is binary, but that formula could apply to multi-class. So for the moment, let's assume let's say x is let's give them some value. Let's say x1 could get any values, like for example 1, 2, 3, 2, 1, so on. X2 is, let's say, is binary, and x3 is like male, female, male, female, and so it's like a category, right? There's your data is this combination of numerical and categorical features. Now, when we are saying that probability of xi given yi, what do you think is xi in that table?
Record.
A record, right? So we are saying that probability of this record, given whatever is yi could be class k, could be class like 0, 1, or whatever, right? So this formula should be somehow that is going to return the probability of all of this, right? So probability of xi given yi. So because this is a whole record, so we are going to show this as a theta x given y. Again, that on the top stands for the actual variable that you are looking for. On the bottom, basically, subscript, you are basically you're writing the value that you are looking for. So x bar is a value that you are looking for, and k is a class. Okay, so this will return you the probability of x being x bar given y is k. And this is, again, you can present this however you want. You can use that term. This is not a specific thing. We're just representing it this way, so we don't need to constantly write that. Okay, that's just a way of showing the parameter. Okay, so when you say probability of x equal x bar, technically the question tells us that what is the chance I have a record, x1 is 1, x2 is 1, x3 is m, and y is given y was 1. So that's basically what's this equation is going to provide. Now, because these terms, like if you want to write this separated, probability of x1 equal 1, and x2 is 1, and x3 is m, given y equal 1. So if you want to write this, technically this is probability of x1 being 1, given y is 1, times probability of x2 is 1, given y is 1, and x1 is 1, and so on, right? So it's a combination. But in the scenario that we have, we just going to look at it as one parameter per whole record, rather than trying to look at them separately. We just assume that for this record, there is one parameter, and that's the parameter. Okay, does that make sense so far? Okay, so now we define this parameter, and then we define this parameter. So we are going to replace them here. However, this one, that is with respect to a given class, and that's with respect to one vector. So it's not generalized, right? Here we want something generalized. You could pass any x bar, you could pass any y, right? So in order to generalize this, the first one that we're going to start, let's start with PYI, probability of YI. We had in the previous class, how would you generalize a formula for discrete classification? So it can get any value. Like if you have a discrete probability and you want to write it somehow that at each point, it only happens for one of those classes. One expression, right? Similar to a Bernoulli, binomial, multinomial, all of those, right? So yi, we know that a point at each time could belong to one class only, right? So you want this formula to be somehow that if you pass any k, like when I say that, for example, probability of yi equal k or yi equal j or whatever, the formula only going to give you one answer with respect to that class. So, okay, so probability of, let's say we have two classes. This example that we solved in the previous class for the logistic. So this became theta y class 1, right? It's because that's the parameter. One expression, y being class 1 times theta y class 0, one expression, y being class 0, correct? Now imagine this is k, it's just k multiplication, right? So we can write this as basically j from 0 to k minus 1, because we have k classes, theta y j, one expression, y equal j, right? So now that equation doesn't matter what class you're looking for, it gives you the answer that you want. Now, the same thing now goes for this one, right? Here now, however, you have two scenarios. One is that for yi, similar story, yi could be any class, but also for x could be any x bar, right? So probability of xi given yi comes from two multiplication. The second one or the first one doesn't matter. One of them is the same thing that we already saw, because we already have the same parameter, k, right? The other one, we just say x bar, because that could be any x, you know? We don't have any limitation on x, we don't have any cap, like y is from 0 to k minus 1. But for the records, any records is possible, right? So when you are saying that multiplication over x bar, that could be any possible scenario that you can find. So the parameters that you already have, x bar given j, one expression, x equal x bar and y equal j. And this formula basically tells you that if I now ask you that, what is the probability of having a record 1, 1m given y equal 1, right? This formula basically what it does, it looks at across all for the first one, which is over x bar. If we look at across all the records, right? How many of those records has this input? If there is a record that doesn't have this exact same input, the power goes 0 already, right? So it doesn't have any input. You basically that will find any record that has this input, then they basically have also a class of 1. Those records they get to the power of 1, the other records they get to the power of 0, right? So does this make sense so far? We're just basically formulating the this probability somehow that we can use it in a general form. Now, so we basically say that the probability of data set was probability of yi given xi. And we know probability of yi given xi is multiplication of probability of yi times probability of xi given yi, right? So we have multiplication over all the data that you have, all the records, times this term, times the above term. We also have an I indices as we are looking over. So does this make sense so far? We just replace those two formula in the actual term that we have. Question? So now what was the general rule that we have? You collect a data set, right? when you are collecting a data set and you are asking a question, what is the probability of this data set? What is the probability of y given x? What's the approach that you want to use, do you think? What do you want to prove? What technique do you want to use for better? Likelihood, right? Because you collected the data set and you're saying, what's the probability of this data set? What is the chance I have this data set? So whenever you have such a question, you always want to find some parameters that they are maximizing the chance of that data set, right? That happens either maximum posteriorly or maximum likelihood, right? So either of those two, you want to maximize, right? So that means that our goal is to maximize this term, right? So what do you think? What's the next step should be? Exactly. Anytime you have multiplication, it's difficult. Half by log, it will work. Okay. So half by log. This basically tells you our goal is to maximize. We have by log here is going to be the summation. So log, this power comes behind. This multiplication also is summation. Now that multiplication also will apply to this one. So it becomes the summation and summation. So now, what I'm going to do is that, so anytime you're doing this maximum likelihood estimation, maximum posteriority, after applying log, as much as possible, you will try to manipulate the terms to simplify it, right? So one way right now to simplify this is, you agree that if you have multiple summation, you can swap the order of the summation. Doesn't matter, right? So I'm going to bring summation over i's inside, basically I from 1 to n. For the second one also, I'm going to bring this, swap the order basically. Okay. So now, one expression yi equal j. What's the meaning of that?
The class is j, it will be output will be 1.
Basically, it tells you that if the class is j, return 1, else return 0. So what do you think is the meaning of this? Summation over all points, one expression.
Number of j classes.
Number of points in class j. You are basically, one expression tells you that if it's class j, it would return 1, otherwise 0. If I sum over all of that, it becomes summation of 1s plus 0s. So 1s stands for points in class j, right? So this term is mj, number of points belongs to class j, right? Now look at this one. What's the meaning of this? One expression, xi equal x bar, yi equal j. What does that tell you? Just that one expression part.
All the records where classes j.
any records that the value of record is X bar given the class is J. So if you look through all the data points, that becomes all the records belongs to class J, they had exact same value X bar. Right? That means if I look at the data set, any record that X1 was 1, X2 was 1, and X3 was M. And it belongs to class J. So you can call this basically this term NXJ, right? The reason I'm calling it NXJ and NJ is to just get rid of that summation. We already know the meaning of it, so we don't need to keep a summation also. So now we basically come to this part. So we are trying to maximize this term NXJ log theta xy J plus NJ log theta y J. Right. So our goal is that now to maximize this term. Now, I'm going to introduce one theorem. That we just need to memorize. It's a theorem. We have a theorem that says that if you are trying to maximize a term, let's say J from 0 to P minus 1 or P whatever, Zj logarithmic Aj, okay, where summation of Aj's, where J from 0 to P minus 1 goes to 1, and Aj's are greater than or equal 0. If you have such a problem defined, you have this objective function and you have this following constraints, the optimal value of Aj becomes Zj divided by summation of Zj's. Let's call it the A from 0 to minus 1. This is a theorem, problem basically, that if you have any problem defined this way, the optimal value for Aj comes from this formula. Now we are going to use that here. Now, the first thing we want to see that is that if can we use this? Are they the same basically definition? Let's start with this one. So we are trying to maximize NXJ log theta xy xj. Because we are trying to maximize two terms, right? So technically you can maximize them separately. That's the same thing. So now that's the objective function. So it should subject to, now, what is theta x given, what is this term? Theta x given y. What's that term? Probability of x. Probability of x given y, right? So do you agree this term is always greater than or equal to 0? Always positive is a probability, right? Also, if it's a probability with respect to class J, do you agree summation of these values over x bar goes to 1? Summation of bunch of probability should go to 1, right? So that means summation of theta x y x bar j is also 1. So that's the same theorem, right? So if that's the case, that means theta xy x bar j, the star, comes from Zj. What's Zj here? Nxj, right? Nxj divided by x bar Nxj, right? The property. So Zj here is Nxj. And summation over here, we have summation over x bars, right? Because the summation over x bars goes to 1. So summation over x bar. What's the summation over x bar and xj?
Total records in J.
Exactly. That's total records in class J, irrespective of what is the x bar. So n xj divided by nj. Right? Isn't that intuitive? It's intuitive, right? So the basically the probability, the parameter that you want to find for a given input, for input given a class, it's simply count how many of that records you have seen in this class divided by how many total points you have in that class, right? So now let's go for the next one. So we want to maximize this term, maximize. Nj log theta y. What was theta yj? Is a prior for a class J, right? So that means that it's always positive, and summation of all the priors should go to 1, right? If you have K class, each class has a prior, summation of all becomes 1 because it's a total data set. So because of that, that means that you can calculate this also as Nj divided by summation of J's, which is basically Nj divided by total points in your data set. Which again is something intuitive. Yes, we already knew that. In order to calculate the prior, what you do, you basically divide the total point in a class over the total data set that size you have. So you guys are like, okay, so we knew all of this, why we are formulating, right? Now, let's see why we are doing this, like why we want to know. That we basically we found this data, like it was intuitive to you, but because you have heard it somewhere before, right? And that heard before comes from this proof. Now, so this is the general form of generative classification. The parameters will be calculated this way. Now think about it. Let's say I have a data set has each record basically has d dimension, okay? And I have let's say I have overall actually I have n by d, right? And y belongs to class y0 all the way to y k minus 1, okay? Now, let's say, I mean, we are looking at the discrete scenarios, right? Examples that also work because it's discrete, we are not doing continuous here. So let's say each of the dimension that you have, each column, can get m unique values, right? So that means that if you have this data set, basically, x1 through xd, each of these x's basically could get m unique value. Each column, they're not the same, but each column imagine can get m unique value. Now, let's see how many. Let's see. When we want to solve this, what are the parameters we need to find? So we need to find for prior for class 0, prior for class 1, all the way prior for class k minus 1, right? So how many parameters? K parameters, correct? That's what prior we need to learn. Now let's go to the posterior. Sorry, like it. So we need to xy, x bar, let's say class 0. Now, when we say x bar class 0, x bar is one unique record, one record basically, correct? So if you have a data set has d columns, each column can get m value. How many unique rows you can have?
To the power of
m to the power of d, right? If you have a d column, each column gets an m value. You have m to the power of d combination. That means x bar could be m to the power of d unique values. So that means you need to learn for this class, you need to learn m to the power of d parameters. Does it make sense? Okay, m to the power of d parameters. If you need to learn m to the power of d parameters for one class, how many total parameters you need to learn? For one class, you need to learn m to the power of d parameters. How many total parameters you need to learn? Okay, m to the power of d, right? That's the complexity of this problem. You see? So, generative classification is simple when you think about it. Calculation of it is simple. It's just you count and you divide. But it's super expensive. You need to find k, m, or d basically parameters for one classification. And now imagine if you d the number of basically the dimension that you have is like million, right? So this is going to be super expensive. Now, what we want to talk about is naive-Bayes classification. So naive-Bayes classification is basically a special form of generative classification. But remember, naive-Bayes is generative. That means that the term of naive-Bayes also has always a prior and light-Bayes, so it's generative. So it's a special form of the generative classification where we make one strong assumption. Okay. Strong assumption. What is the strong assumption that we make in naive-Bayes?
We assume that the features are independent.
Right. So we assume that each column that we have, or basically all the columns are independent of each other. So features are independent. Okay. Now, before we try to formulate it, let's think about naive-Bayes. So naive-Bayes is a really well-known, well-accepted classification. It's really common in like banking industry, healthcare industry, because it's easy to interpret, it's easy to understand. You know, it's pretty quick. You know, naive-Bayes is really quick for calculation. We will understand. We will see this later why. And think about one example. So, like for so many years, naive-Bayes have been used in majority of this, like email services, Gmail and stuff, for the spam detection. You know? And these days, some of the companies might have moved to like deep learning. You never know because they don't tell you what's the algorithm. But it's possible that it's still also using naive-Bayes because it's super cheap and it's super accurate for those type of tasks. Now, think about it. You have your basically your task is to create a classification model that looking at the document tells you if the document belongs to sport or it belongs to, I don't know, like education, or it belongs to like economy, right? So the naive approach, or basically the really basic simple approach, is that you create bag of words, right? You divide the text into words, right? And you basically assume each word is one column in your data set, right? So each word is one unique feature. Now think about it. If I'm trying to say if a document is a sport versus a document is news, if I already have seen the word soccer or football, Does it matter if the word ball or the word referee comes somewhere after? No, because you already know this document that they are independent of each other, right? So that's why in a lot of text classifications, as long as you can make this assumption that the words are independent of each other, you can use names, because in order to make some sort of the classification, it doesn't matter. But in the general generative form, let's say you are trying to do a task where you are trying to do something like name entity recognition, for example. Right? Name entity recognition is if there's a text, you go over the text and you say, this is a name, this is an organization, this is basically ID, this is a medical ID, so on like that. You tag each word in a document with a specific like an entity that you are looking for. In the scenario like that, the order of the words are important, and then the relationship between words is also important. So you can assume that the words are independent of each other. But if I want to make a classification that all I care about is that if it's spam or not spam, if I know there is a term in the document that says that call for free discount or something like that, doesn't matter what else comes, automatically that email service will send it to a spam because it says, oh, I have seen this word, doesn't matter what else, where else is coming, right? So naive base, we make this assumption, features are independent of each other, okay? Now, if we say features are independent of each other, if we want to look at this, what is the probability of X bar given Y is J? Features are independent. That means we don't have probability of X2 given X1 anymore, right? So this is simply a probability of X1, that's dimension 1 has this value, times probability of dimension, let's put I here. I stands for data point, and this stands for student. Okay, nice, right? Which is multiplication of probability of xi of this I e. Let's write the different indices. So this is E for dimension, P. This is simply multiplication of all of those terms, right? Now, let's look at the previous problem that we were trying to solve. In generative modeling, we say the probability of data set was and because this is generative, this comes from likelihood times prior, right? So now for this term, let's start with the first one. So we are trying to write this as this is going to be, let's start with the k first. So we have k from 0 to k minus 1 classes times, we no longer have x bar because x bar was considering whole record, right? Now we have that p from 0 to dimension of the number of columns that you have. It's going to be p from 0 to p minus 1. So that should be. And that term itself, now it has basically a theta, same thing, theta of xy, x bar j, so this e one expression xp minus right. So the only thing that changed, we removed that x bar, rather than because x bar was for one whole record, right? Because now they're independent, you don't care about whole record. The whole record will be represented this way, right? So, does this make sense? Anyone here thinks that it doesn't make sense? Want me to go over it? Which part of it?
Last.
This one?
Yeah.
So, you agree this part? Up to this part?
Yes.
So, probability of xi given yi. This is probability of xi being x bar, right? Given yi equal j. And we say x bar is no longer as x bar because the features are independent. So the probability of x being x bar is multiplication of probability of first dimension get this value, times second dimension get this value, and all the way to the end, right? So that means that multiplication over all the dimensions, each dimension get a value given class is j, right? But that's only for one class j. So if I remove the class j from this equation, probability of xi given yi, right? That means I don't have a j anymore. So I need to have two multiplication. Once I loop over all possible j's, and once I loop over all possible dimensions, right? Probability of xi given yi, correct? So probability of xi given yi, we say that rather than just showing it that way, we use the term theta xy given x bar y, right? So this p stands for which dimension we are looking at, which column we are looking at. J stands which class we are looking at. And there is a one expression because still at each time, one of them will happen, right? Does that make sense? So this term becomes for the likelihood, and prior doesn't change. It's the same as what we had before. Make sense? So, same thing that we did before now, basically. In order to simplify it, basically, apply log to this, apply log. So, I already take I from 1 to inside, so this becomes I from 1. And -1 expression. So this one on top, sorry. By log here. After I only log that goes behind. So First thing we said, okay, this one doesn't change, right? It's the same. So this term we already solved it. That theta yj star is points in class J over all points that you have. The prior doesn't change, right? It doesn't matter, naive base or whatever. Prior is simply count how many points in each class, divided by total points that you have, right? Now look at this one. So this term, so we know how we are going to solve it, right? That theorem that we wrote, right? So actually I'm missing something here. Yeah. Okay. We have one expression, x I p v. So log theta. We know theta xy x bar p j star equal this term, which is summation I from 1 to n, one expression I p over it's becomes, yeah, simply becomes the n j, right? So basically, what's this term says? If you're looking at the column, and imagine we have this column which is x1, and it can get term m, f, c, and so on, right? We want to find what is the probability that you have a C given class 1, right? So all you need to do is that count how many C you have in class 1, right, which is that term, divided by total point in that given class, whatever is the class, right? Depending on which class you are looking at, NJ, right? So you simply basically count how many points you have where that column has this value over the total points in that class.
Wouldn't it be n xj?
And
Or
yeah, and
X bar.
Right. And xj. Right, that same column. Okay, and yeah. So basically, total points you have that has exact that value divided by total points in that. This gives you the same thing, right? Let me see. No, so it's nj. What you are saying actually, what you are saying is this. If you sum over all this, which is the same as nj, no, all points in class J, right? So now everything seems the same so far, like generative, except that part, right? Now let's see what's the impact of that. For the same scenario where x due data set has n by d columns, and each dimension can get m values, right? We want to see that how many parameters we need to learn. So, and y also basically had k classes, right? Yk minus 1. So for y, basically you need to learn k parameters. Right? For the prior, you still need to learn k prior. But for the likelihood of x given y given dimension p, and this is value j. Okay. How many you need to learn? M. Right? Each column can get m unique value. So I'm looking at for one column because the columns are independent, right? So I will learn m parameters. How many of this I need to learn? I have d columns, right? So you need to learn m times d of that. How many class you had? K. So the total becomes O M K D O O K M D. Correct? So that's linear. Previously was O K M bar D. Right? So you see in naive Bayes, by simply making an assumption that the features are independent, you reduce the complexity of a model to the power of D, right? To a linear combination or linear complexity. Does that make sense? Again, this part, if you're not following, you have D columns. Each column can get M values. Columns are independent, right? Each column, we know for each value in the column, you need to learn a parameter, right? So it means that if you have M unique value in a column, you learn M parameters. You have D columns, you need to learn M times D parameters. You have K classes, M, K, M, D parameters. If they weren't independent, you needed to learn M bar D combination, right? Question.
When you said if they weren't independent, then how many do we need to learn?
M to the power of D, right? If you have D columns, each column can get M value, but they are not independent. You will learn M to the, basically that's a combination. You have M to the power of D combination input that you can have. Okay. Now, think about it this way. We wrote all of this, and if we think technically, it's all intuitive, right? All you needed to know, basically, I could have just come to you and tell us that all you need to do is that, all you need to do for generative is to count divided by total. And if it was naive Bayes, assume that they're independent when you're doing it, right? But in that scenario, you never would have learned that if you go somewhere and someone asks you that, hey, why do we do naive Bayes? What's like if someone, you go to an interview, imagine someone tells you, why do we do naive Bayes, right? And how does improve the learning? Now you can't answer. It's simply just saying that the features are independent. It doesn't give you that. Okay, what's the benefit of that, right? Does it make sense? But otherwise, it's intuitive. Like I expect that any of you right now, you don't even need to memorize any formula here. You simply should be able to do naive Bayes. By just look at each column for each value, count how many you have divided by total in that class. You have the parameters. And repeat that for all possible. Write a couple of for loops. That's the parameters for the naive Bayes. For the generative modeling, the other way around. You look at each unique rows. How many of this row I have? Divided by total, put in that class. That's the parameters that you need, right? Now, let's make one, let's solve one example. Let's say you have this data set. So 1 and 0 stands for the class And I'm going to add some dimensions here. So this is dimension 1 gets a value 1, dimension 2 gets a value 1, dimension 3 gets a value 1. That means that is a table of 3 columns and binary classification. Zeros. So, okay, so you in your exam also you're going to get questions like this, but not as simple as this. But I'm going to give you a data set like this. Now we'll ask you that to solve for finite parameters and then apply to some test data set, test data that you have received, you have given, and make a prediction. Now, you are given this data set, and you are told that you need to solve this using naive-Bayes classification. So, first thing you know about naive-Bayes is generative, right? You have a prior and you have likelihood. So, how many classes do you have? So, remember, also you will see when you want to code naive-Bayes, this is one of those questions that you need to beforehand think. How many classes do I have? How many priors do I need to learn? How many likelihood do I need to learn? You need to have some idea of how many loop basic you are going to write, right? So you have 2 class, that means 2 prior, right? So write down your parameters. So I need to learn a prior for class 0, 1, a prior for class 0, right? So what is the prior for class 1? So, right, you have 4 points belongs to class 1 out of 7. And the other one is 3 by 7. So, let's set up this class information. Now, okay, likelihood. How many likelihoods do you need to learn? For class 1, let's say this way. When we wrote the complexity, what was the formula? 6, right? It was m times d, right? How many d you have? 3. All dimensions are binary. So m times d, which becomes 6, right? So let's start from the first one. Let's go over the dimension 1. So what is the probability that dimension 1 gets a value 1 given the class was 1? We know that then the other one is basically if dimension 1 gets 0 given class 1 is going to be 1 by 4. Then you go for the second dimension. What's the probability of dimension 2 becomes 1 given class 1? 0. That means probability of dimension 2 becomes 0 given class 1 is 1. And how about the dimension 3? Actually, let me add some indices here so we can follow that. 1, 1, 2, 2. What was the number? 1 by 2. And for dimension 3 becomes 0, 1 is also should be 1 by 2. Right? So those are the parameters that you need to learn for naive-Bayes. Now, what's the probability of having 1 given class 0? Two by 3. 2 by 3. 2 by 3. And 1 by 3. What's the probability of dimension 2 being 1 given class 0? That means the probability, no. And what's the probability of dimension 3 becomes 1 given class 0?
2 by 3.
By 3 is the other one is 1 by 3. So now before, so this is basically what, when we say solve a naive-Bayes classification, this is what you learn. This is your model. Okay. Now, before we apply this to a test point, if a distribution, if the shape of a distribution is defined by its parameter, what type of distribution is that? Parametric, right? And non-parametric was the distribution that the shape of it changed with respect to data set. Also, we say that we have the same thing for models, parametric modeling, non-parametric model, right? What was a parametric modeling? A model that the shape of the model is defined by the parameters, right? Linear regression, logistic regression, the formula, if you have D dimension, you have D parameters, right? Non-parametric model is naive-Bayes. The more data you have, the more parameters you need to learn, right? It doesn't matter what is the dimension. It's related to the size of the data set that you have. The more data, the more parameters. For any model you have this like this, that the number of parameters that you need to learn increases as the size of the data increases. That becomes non-parametric model. Okay. Now, let's say I will tell you that, okay, you have this test point, and I ask you that, okay, which class this belongs to? What would you say? I leave it to you guys. What's the formula do you think you need to use for making classification? But what's the formula you're using?
Formula for classification.
Yeah, here.
P of x given y into P of y.
Exactly. Likelihood times the prior, right? So let's say you want to find what's the probability of class being 1 given x test, right? This is what you're trying to solve. The first thing is that, okay, you multiply a prior. So what is the prior? 4 by 7, right? Times. The second becomes, because you're independent, class dimension 1 being 1 given class 1 times dimension 2 being 1 and times dimension 3. So dimension 1 was 3 over 4, dimension 2 is 0, dimension 3 is 1 over 2, which, as your friend mentioned, goes to 0, right? Now, one thing that's really important, you shouldn't make this mistake. In generative classification, if you calculate one class, don't do one minus the other one. They are not completing each other. In discriminative, you calculate the probability using some sort of sigmoid function and stuff like that. It squeezes, you normalize the value. You remember softmax or sigmoid, you normalize the value. That's why they sum to 1. Here, the priors, yes, they sum to 1. But the likelihoods, these terms, these are from 2 different subsets of data. They never sum to 1. And you are multiplying series of probabilities to each other, right? So they never should sum to 1 unless you normalize it, right? So that means you need to calculate being class 0 given x test. And that's also 3 by 7, 3 by 7 times 2 by 3 times 0 times another 2 by 3. That also goes to 0, right? think about it. If you see something like this, now if this is a question that I will ask you. We have this probability, and you make a test point where the test that both class goes to 0. That cannot be correct. You need to give one class, basically, right? How would you fix this problem? Which one of these two you think is larger?
First one.
Last one. First one. How do you say first one?
It's the priors.
In your
The likelihood of first one is more.
The more cases in class 1 rather than class
no. The probabilities goes to 0, right? You multiply them, doesn't matter what's the prior likelihood here, it went to 0. That 0 is a bottleneck in your problem. What do you think is the best way to get rid of that 0?
That's more.
Maybe, yeah. So anytime you have a problem like this, you need to smooth the function. That means that you need to account, what if I had a point like 1 that I never have seen before? What should I do then? The probability of both class goes to 0. One simple approach is that anytime you have a 0, replace it by whatever you want, a watermelon. Seriously, this is going to be what? 4 times this 2 cancel is going to be 3/14 multiplied by a, right? And this one is 4/21 multiplied by a. Now, which one of those two are larger? Three by 14 versus it's almost 2.
One is larger.
Large, right? Doesn't matter what's a. A could be anything. Correct? So this is called smoothing. Okay. Smoothing technique. Smoothing technique basically says that when you are calculating this likelihood, these priors, basically, but priors not because we have all the classes, the likelihoods. For each point, if you never have seen it before, assume either something, a really small value. It's just not 0. It could be 0.00, but for all of them, assume the same, right? So that way you will have the same. Basically, you will have a formula that you can still make classification.
So for both zeros, we have to assume the same.
Because you are doing always the same thing, right? So
We cannot make sure that both can be assumed as the same. Okay, here because it's 0, we are assuming.
So here, because these are 0, right? You put an A. Anytime basically you have a 0, just put an A, something the same. Now another approach, which is that's a simple scenario. Now there is a formula that is the most common being used. It's called Laplace smoothing. Right? It's like well known, well accepted in the field. Laplace smoothing basically says that in order to find this theta for a given dimension, this is what we did basically, right? We said this is equal. Looked over all. First one was dimensions. We write we are only talking I in J XP XP, right? With the naive base. And then we add this over and all the points in class 5 from 1 to n. And we divided this over NG, right? That was the term. How many points in class J, column P, has this value? Divided by the total point in class J. In this scenario, we look at how many points in class J, column 2 has 1, none, right? That's why 0 divided by total point becomes 0, right? Now, Laplace smoothing says that when you want to calculate this, add the value here, tau. Tau could be whatever you want, like 2, 3, 1, 0, not 0, like 4 or 5, something, right? So if this is 0, it's not going to be 0 divided by it. You always have something, right? Does that make sense? But there is a problem here. If I simply just add, let's say if I just add 3 on top, right? So 3 divided by nj, what's the problem with it? Right, it goes up. So imagine for some of the, basically you are keep adding some value, a constant value for any value that column can get. For example, for 1, you count how many 1 I have in class, in dimension 1. Okay, how many value of 1 I have? You had 4, imagine. And total class, point in class 1, maybe it's 4 also. So 4 plus 7, that goes above, right? So when you smooth, you need to also add something to the denominator to be sure that it increases with the same ratio, right? Now, the difference here is that you multiply it by m. Why? Because each column can get m value. You need to increase each value by same amount. So your data set basically with the same ratio increases. It's not like that you just keep increasing 1, right? So this is called Laplace smoothing. Does that make sense? So when we code the neighbors, you will see that. So in order to avoid that going to 0, you basically write one function, Laplace smoothing, basically anytime and that tau is a hyperparameter, you decide on it. Doesn't need to be anything specific. 2, 3, something that doesn't go to 0 is.
But if the values are in probability, right? So if we add certain values, say even 3 or 4, can't they change the outcome a lot, or they won't?
No, we increase everything with the same ratio. This is total numbers. For each, we are looking at one column, column P, right? Column P can get m unique value. For each value, when you are trying to calculate this data, you add the tau on top, right? So all the values in that column increase with the same ratio, and you're dividing it. Total data set plus, if I have three unique values that this column can get, and my tau is 3, I add 9 total data point to that class. That's what it means, right? The original points that class had plus 9 new data. And that's the reason we do this is that so they all increase with the same ratio. That probability concept that you are saying that it doesn't change. It's the same. You only don't get 0 anymore. Does that make sense? Question on this?
Does it matter like how many zeros you have in terms of like data? Like it doesn't. It's just like the final thing.
When you are saying how many zeros you have, is that how many of this goes to 0? That doesn't matter. You can always smooth the missing. Yeah. And that's something that if you think about it, if you do something like let's say we talked about the spam detection. The first time when the Google, for example, creates this naive-based classification, they said they go over thousands, like billions of emails, right? And they create this bag of words of all possible words that are being used, right? Now, let's say a couple of years later, new trends comes in and all these new words coming to emails. You always see 0 for all of those. Doesn't matter how many new words comes, you smooth them. Right? So that's also the beauty of the naive base, because they're independent of each other. The impact is not important, right? If it was a combination, then you're going to have a lot of problems because it's much harder to always look. Oh, I don't have it. Right? So it's much more difficult for a generative versus the naive base. Questions? Okay, so now what we are going to, so this was for discrete naive base. Now we are going to expand this to a continuous form of the naive base. Right. So now the next version of neighbors we're going to talk about is called Gaussian neighbors, which you definitely will, with whatever company you will work for later, you'll see that it's really common. Gaussian neighbors is one of those common techniques to try for classification, especially when we're dealing with the basically Gaussian continuous features. Like if you have height, waves on this side of like a centimeter, millimeters, anything that's basically continuous, anything that's not discrete. Okay, so now the scenario is that, let's say, basically we are saying that probability of a x dimension is called x. If you use dimension d, yes, or just write the probability of dimension d given y, yi, or it's like in the general form. Well, we want to find what's the probability of dimension d given given two basic classes that you have. So let's just start with this. Let's say we have a binary classification. When we are talking about this type of classification overall, that means that you at the beginning you separate your data. All the class one you put in one bucket, all the class zero in another bucket, right? Now you are looking at each columns of these two separate data sets. And each of those two columns, so this is class one, this is class zero, and this is dimension d, right? Each of those basically come from a Gaussian distribution. And each Gaussian has its own mean, basically. The zero here, mu one, right? And they have their own also variances, right? So that means that this term comes from a Gaussian or m e j. Right? E is the dimension, J is the class. So what is the difference here? In discrete scenario, when you are looking at the column can get m unique value, right? That means that for each column, you can find m parameters, m thetas, correct? If a column has m unique values, x1, this has m basically m values, and this is for all class one. So that means that you need to learn, let's say, xy given x or x1 given 1, you have m of them, right? M of them, right? However, here, for a column given class, you don't need to learn m unique values. It's continuous, right? You are not going to find how many times I saw 3.542. Like doesn't make sense. You have one distribution that you fit that value to the distribution and say, okay, because it's a Gaussian, what's the probability of this value? Does that make sense? So that means the same thing that we had before. If you collected this, if you collected this data set, and this data set y, IID, that means that the probability of all of them comes from this term. And we know this term is the likelihood times prior, right? So it's basically now. So we have k classes, right? each class has a dimension. Basically, we saw this before. From 0 to e minus 1. And each dimension, so, and also this is here, the thing is that you don't have that, basically, you don't need to use that one expression technically, right? It's continuous. You have a Gaussian form here. So this comes from a Gaussian or mu e j sigma to ej times whatever was the prior. The prior still has that. Prior still has that one expression because it's discrete, right? So I apply log. Now, that's a Gaussian, right? Probably by now you know if you apply, it should be easy to apply log to a Gaussian, right? So it becomes log of 1 minus, it becomes minus log of 2p sigma 2p j over 1 over 2. Log and e in the Gaussian, they cancel each other. Minus xi e minus mu e j divided by 1 to ej, right? You just write a Gaussian using this and apply a log to it. That becomes this one. There was a log of 1 and block it. This one? The whole thing. This is negative because it was log of 1 over. Okay. Right, so log of division becomes log of subtract, right? And this is, it was e to the power of negative, so e cancels with the log and negative comes out. So, and then plus to the power of 2. So that makes sense, right? We just apply the log to a Gaussian with that parameters. The given parameters. Now, this is your in-class problem. Your in-class problem is going to be to find mu and variance, basically. You already have this. You don't need to solve that one. It's there. And how do you find them? Simplify it, take a derivation with respect to each them, and you will find those. So that will be posted after the class. Question on this.
This is a parametric.
What was that?
Parametric model.
This is a parametric model. So it still is non-parametric. So the reason is that this shape, this is parametric in Gaussian, but still the dimensions, each dimension individually is parametric, right?
Okay, it's just that we don't have to learn m values in each
Exactly.
dimension.
But it's still, as you increase the data, you know, this terms will change, right? So now, so this is Gaussian neighbors. The only difference is that, you know, you just terms are Gaussian. You don't need to count. This one is skewed. So think about how we're going to solve this. You have a data set. You separate both classes. You look at each column, find the mean and the variance of that column. You simply calculate what's the mean, what's the variance. Can you use any library that gives you the normal distribution? Or you can write the Z formula yourself for Gaussian, right? And fit it to that. After you have that formula, for any point, if you want to find the probability, you pass it to the formula. What's the probability of this value? What's the probability of 3.5? And from the Z table, it will give it to you basically, the function. And that's the value. In the previous one, you needed to write a for loop basically to count, divide. In this one, you need to first find the mean and variance per column and just have one function that returns a Z value with respect to a given mean and variance and given input data point. And you multiply those together in the same way, basically. Right? So we're going to stop here. Let's see, 10 minutes, 5 minutes, 10 minutes break. And then we are going to have a lab on logistic regression. And also, because I tell this because I tell to any other classes I don't want to, I want it to be fair. Be sure you really know how to solve questions manually. You might get the same data set, but then I might ask you that to solve it using Gaussian neighbors. You know, the questions are simple, but if I tell you Gaussian neighbors and give you mean and the standard deviation, I expect you to know, do the rest. You know, that's 10 data point. It's not going to give a discrete. I'm not going to give you a discrete and say that to count. Maybe I give maybe you know it's lucky because every person is going to get a different question. Maybe one person is lucky it's discrete, but the other one is continuous. So just be sure that try to solve this manually, right? Okay. And be sure that you know how to read Z table. I expect you guys know that. Okay. So let's take a break and then.
Very much.
This is the ends and all.
Oh, yeah. You want me to?
No, we can do it together.
When do you want?
I don't know about actually the TA schedule because each TA has a schedule.
Yeah, has their
And you
own.
need to send them.
Yeah.
So I was wondering, like, is this, so I was going to start with your point is non-parametric. So.
Managing dataset, so yeah, it's not only as long as you can solve it for human. You can solve the problem with 3 features also and 4 examples. Then you should be able to solve this.
Okay.
Yeah.
Like it's the same thing, like
Same
once we
thing.
get an idea of how it should, we have to just replace the values. So basically, if I start with close form, then I'm just going to that X transpose X equals which are convertible.
Yeah.
So this is the correct way to go.
I did approach the data set on the last meeting.
Yeah.
Not to what the name is not. So you just have an Excel file. Yeah, the Jupyter. This is just a couple of, it's like a plot function that I will post after the section. You don't need that for the lab, right? So just go ahead and open a Jupyter and import the following libraries. Technically, you don't need the right now. You don't need the plotting ones because you don't have the plotting functions. Do we have anyone here from Thursday class? Thursday. Thursday or Tuesday?
Yeah, the part is long.
Yes, it's like. Good. So now this class that we are importing, this library data classes. In previous class when we wrote the class function for basic class module for linear regression, and we passed all those parameters inside the init. We needed to one by one tag them self dot and with self dot. That's kind of like an old approach. It's something that we don't use it these days anymore. So the optimized way, at least, is that you're going to work with these data classes from Python. So now, what you need to do is that first, from data classes, import data class. Anytime you want to create a class now, before the class, you will write this @ sign data class. Okay. So Python also has this thing that, if there is some specific terms, you could add sign and those terms behind function or behind the class, it connects them to that module that you are trying to basically this. If you put behind the class, you put add sign data class. It tells that it says that this class is an instance or is basically a version of that data class. So that's the meaning. So we want to write, moving forward, our classes, any class that we are writing, use as a data class object. Now, what is the benefit of writing that? Before actually I write the benefit, first, we want to do logistic regression, right? So, did any of you guys thought it beforehand for coding this? I told you guys in linear regression that for the next class, think of how would you solve it beforehand. No one. Okay. How many ways you can solve logistic regression? One way, and this is gradient descent, right? Okay, so it's gradient descent. What parameters do you need? Okay, max iteration. What else?
Function.
No, those are not parameters. What are parameters? Epsilon. What else? Learning rate. Learning rate. Data is what you're going to learn. So the way you need to pass to the model, right? So And okay, those are all you need basically, right? Now, what are the functions that you need to have? You need a loss function, you need a cost function, you need a derivative. When we want to solve logistic regression, what was the probability of y being class 1 given x? Sigmoid, right? Sigmoid over this term, right? So what does that mean? You need a sigmoid function. Sigmoid. The probability for class 0 is 1 minus, so you don't need to write that. Now, let's start with those ones. So, first part of the class is always the parameters that you are passing to the class, right? Now, when you are tagging this with the data as a data class, you don't write the init anymore. Okay, that function, it doesn't exist anymore. What you do is that you simply start with writing the parameters that you want. So max iteration, that's the first parameter. And this is going to be an integer. We'll go to the next one. So you need to write the name of the parameter and what's the data type that parameters will receive. Then you have learning rate, and this is going to be float, let's say 64. Just with float actually. Just with float. And then you have epsilon, which epsilon is the tolerance, in case you forgot, epsilon is the tolerance. That's also a float number. Now, one other thing is that I want for this class that also has an option that user pass the address to the data point. Like user has a data set, whenever they want to initiate this class, they pass this parameter also the address to where is the file on the hard drive. So we will have file paths. And that's also a string, right? So now, what will happen here is that because you're creating a data class by default will pick any variables that you have here and tag it by self. So you don't need to write self dot anymore, you know? Okay. Okay. So you will basically tag all of those with self. We will tag all of those with self. Now, one thing that here you want to add is that, so the data class has, I definitely recommend you as of search for this data class in Python. This is from the main Python source. And go take a look at the options that you have. The reason I tell you to do this is that if you want to improve your coding, stay on top of what's out there. Always review the Python library itself. You don't need to basically go through everything, but you will get some idea of how is the version of coding, how programmers actually code. And data class, just go through it. You will see a couple of examples. It has good examples of if you want to have an input as a list, how should you pass it? If you want to have an input as simply like that, right? Now, the other thing here is that, okay, there is so we don't have init, but we have another function that if you want to add, it's not necessary, but it's called post init. Okay. So post init, think about the naming is also really intuitive. So init was whatever is init, right? Post init, that means that after the init, what should happen, basically, right? Now, post init has this property that whatever you write in it, like whatever code you put here, the moment the user initiate the class and pass this, that will execute without any need for user to tell them, right? So if there are some steps that you want to be sure that as soon as I get the data, normalize it, add a column 0, whatever, put those posts in it, and it will definitely, it will basically do those for you. And then user later can just simply call fit function, right? Or you could even put the fit here. Like user just call this and it gets the answer. You know, you basically you define whatever you want to be automated, right? So post in it. Now, for now, I will do pass because we haven't wrote the function here. Now, okay. What are the functions that we want to have? Because user is passing the file pass, so we need a function that reads that file, right? And return the values in the proper format. So we create one function, data reader. Okay. So this data reader basically, now later you need to tweak this to make it better because like what if the file is CSV, what is the file is text or whatever. But for now, I know the file that we want to use is just Excel file. So I would just say X or train data frame basically is pd dot read Excel. So self dot file pass. See, already file pass, it automatically had the self associated to. And so this pandas read .excel, because your Excel file has multiple sheets, you need to pass what is the sheet that you are trying to read. Okay, so it has a parameter called sheet name. And I think for this data set, the name of the sheets, if I remember it from yesterday, is 2005. This
It's 2004, 2005 data.
data, capital,
Capital.
are those spaces correct?
No, there's no space between dash and 2000.
Okay, so thanks. So that's for train data, and for test data frame. Excel, that's file pass. And 2000, or is it 2007?
Yeah.
Dash K. Okay, now. We can. So this is that's a data frame as a pandas data frame. We don't need it as pandas. We want to convert it to a NumPy matrix, right? And we want to separate it. I think the first column is classes. Column 0 is the class, and the rest is the input data. So we can say X, or let's say train X, and train Y. These are simply your, if you do train the values, and then the values we said after pandas, if you do that values, it converts it to a NumPy matrix, right? And I know the first column is column Y, so I pick all the records and all the column from the number ones. I drop the 0. So that becomes my train X. And for Y, basically, I will pick the first column. That's 0. And you repeat the same thing for the test. Test X. And then we return train X, test X, train Y, and test Y. So this is the This is the first function that we have. So this function basically is read the data. Now we know this function's job is to get the data, and we don't want you data to call it. So we will put this, we will call to this function inside the post init. So as that means that as soon as you user initiate the class, we will call to this function and get this value. So self dot data reader. Now you need to tag all of these values with self so we can use those. Now the next function that we need is still we want to have a bias term. So we will add a column 1 at the beginning of our data. That's not technically necessary always, but it's good always to have a bias term and let the model to learn. If it is necessary, it will learn. If it's not necessary, the model will not learn. So we want a function that when it gets a data set, that's basically adds a column 0. So and we can call it also here. On the same this point also. Okay. So that's the first part of the work, right? So we have this class. As soon as being initiated, it will read the data, and it will also add a column of 1 to both string x and test x. Now let's look at the functions that we need. So the first function, if I'm looking at this and I want to see that, okay, what are the functions do I need? I know the first thing that I need to have is a sigma. Because for a cost function, for the derivation, you need to first have the sigmoid, right? So I will start with the sigmoid function. So define sigmoid. And sigmoid receives z as an input. Z is not x anymore. Remember, what's sigmoid received as an input is theta transpose x. And for now, we assume there's something called z, whatever you want to call it. So what's the formula for sigmoid?
1 plus e.
1 or over 1 plus e minus z, right? So if you want to write that basically, you will say to just add it here. The sigmoid value is 1 over 1 plus np exponential the power of minus z, right? And you want to return that sigmoid value. So, okay, that's a sigmoid. Now, how do we generate z? Z comes from theta transpose x, correct? So that's a predict function, right? So let's write the predict. And predict basically it returns x dot self dot w, right? And look what sigmoid received as an input, theta transpose x. As soon as you have the theta in classification, you find that value, pass it to a sigmoid, it tells you which class, right? We call that as a predict. Now, okay, what else do we need? Now we need to go over loss and cost functions. Now, there's a part here we want to iterate over. Now, in our class, basically, when we wrote the cost function, we reached to a term which we were maximizing, and we say that we can solve it by minimizing of that term, right? So we wrote L W to be minus this was JW, sorry. JW to be minus LW. The likelihood was we multiplied it by negative, right? And this term become for all points, you are calculating log of 1 plus e to the power of theta transpose xi minus yi theta transpose xi. That was the loss function, right? And we wrote a derivation for this. And that become basically summation xi times the sigmoid theta transpose xi minus yi, right? And I told you that based on the sign, it tells you the line to go down or up. Now that's the cost function. There is one other cost function that you need to know. It's called log loss, or binary cross entropy loss. Okay, so this is one of the common loss functions that we will see in binary classification. It's called log loss or binary cross entropy loss, and it's common that someone asks you a question on this. Also, remember that they ask you to explain this loss and how does it work. Now, the way that binary cross entropy loss will work. So let's say this is the bar that we have. So this is the probability that we have, and this is the cost. So probability goes between 0 to 1, and we say that we always calculate everything with respect to class 1 technique, right? Now, we are saying that we're going to have this loss function. And it's going to look like this. For points that belongs to class 1 or for the points that belongs to class 2. First thing is that in regression, you only need one loss function. Every point is this minus whatever to the power of 2 or absolute value. But in classification, you can't do that because you have two separate classes. Each of those classes have a different error, right? So you need to have two terms. Is it for class 1 or is it for class 0? So for class 1, we are basically calculating minus log of theta transpose xi. Theta transpose xi basically it's the value that you get for class 1, right? Oh, sorry, a sigmoid of that. And for the other class, you will have minus
Subtracted by y.
No. This is the loss function. That's what you're talking cost function. I'm going to expand this. So what is this loss function tells you? If the point is class 1, after you make a prediction, the error comes from a negative log. What's the negative? Where is the negative log? Log is on up, right? So this is a negative log. If point is class 1, that's a negative log. So this becomes, if it's to the closer to 1, what's the loss? 0. The probability closer to 1, the loss goes to 0. That means that if the point belongs to class 1 and you predict 1, what's the error? 0. The point belongs to class 1 and you predict 0, the error is infinite, right? Now for the other one, is 1 minus that, so this becomes for class 0. Log of 1 minus. Okay, so this one tells you that if you are predicting for class 0, if you predicted the probability becomes 0, that means correctly, the loss is 0. If it's class 0 and you predicted class 1, the error is large, right? So that's these two forms. So if someone told that what's a log loss or what's a binary log cross entropy loss, it comes from these two formulas. You just basically apply log over that's why it's called log loss. You apply log over the term that you're predicting, for always with respect to class 1. With respect to class 0 becomes 1 minus class 1. And that's the term, it's a negative, right? Now, if you want to write this for all the points, this becomes summation over all points, yi log minus yi log minus 1 minus yi log of 1 minus. At a given point, one of these happens, right? The other one, if the point is class 1, this term goes to 0. This is because 1 minus y, right? If the 1 minus 1 goes to 0, this term goes to 0. So you only have for class 1. If the point belongs to class 0, you don't have an error over class 1. This goes to 0. You only have error over class 0. So this is the same thing we use it in formulated somehow, that at each given point, this is kind of basically using the one expression technique, right? So this is called binary cross entropy loss log loss. There is no difference between this and this. These two terms are exactly the same. Here, you directly writing it with respect to class 1, right? So this term, if y is 0, right? This goes to 0, you have this value. If y is 1, you have this term basically. And this 2 giving you the same thing. Okay, so don't confuse them. But the reason I wrote this log loss and binary cross entropy loss is more common that you see this one being used, this one being formulated, that. And we're going to write both of them to see the differences basically. Does this make sense? So binary cross entropy loss and log loss. Now, before we write also, these losses, we need to talk about evaluation right here. So in regression, evaluation was straightforward. You actually simply deduct the points and you calculate the overall average error, right? In classification, is not like that anymore. All right. So now, when you are making, we are talking about the binary classification, right? When we are making a binary classification, you have two classes, class 1, class 0, right? So if you are looking at this square that we have here, the circle, this circle, are all the points that your model say these belong to class 1. Okay, circle is all the points that model says belong to class 1. The green side of the circle are all the points that they actually belong to class 1, true positive. The right side of the circle are the points that they belong to class 0, but your model said they belongs to class 1. Outside this part, false negative, that means the point that belongs to class 1, but your model says they belongs to class 0. True negatives are the point that belongs to class 0, and your model correctly say they belongs to class 0, right? So there are 4 scenarios. Now, why we are talking about this? The reason we talk about this is that if you want, what metric do you want to report? What metric you want to say that if after you learn, how good is your model?
Yes.
Accuracy.
Sensitive, depending on the class.
Yeah, that's depending. What else? Precision. Why precision?
The number of points it is correctly classified.
Right, but precision tells you the number of points you correctly classified. Doesn't tell you that the number of points you missed, right?
Is F1 score?
It's according to the class of interest.
So now let's do one thing. So don't need that, right? I need this, right? Yeah. First, why accuracy is wrong. The reason you shouldn't use something like accuracy is that imagine I have like a model that is working on a really sensitive scenario. A sensitive scenario could be like you're working on in NASA and you have this satellite, and this satellite goes by a millimeter out of the orbit. That's going to hazard some huge impact later, right? And your model job is that to detect that one movement, right? But that movement is something that you don't have a data with. Like maybe you had only, let's say I have 100 data points that I have collected. One data point shows that if the scenario is that you're going out of orbit, 99 data points you are not going out of the orbit. Now, if you develop the model, what's most likely for your model to predict? If you develop a model that always, because 99 times it has seen is not going to happen. If always your model said it's not going to happen, what's the accuracy of your model? 99%. But your model failed to do the task. See? So accuracy is the worst metric that you can use, because you can have an accurate model, but it doesn't learn anything, because especially if there's some imbalanced scenario in your data set. Okay. So accuracy, just drop it from your list, don't use it in your project and stuff like that. Okay. Now, then we are going to over precision and recall. Precision says that if I have predicted 100 data, let's say we have this data set has class positive and class negative. We have 10 points class positive, we have 90 points class negative. Okay. Now I'm going to ask you this question. Let's say we make like three models, right? One model is like a model A. It basically says that there were 10 points class 1, 90 point class 2. And you have model B, basically says you have for class plus you have 8 of them defined. For this one you find 92. You have model C that says I found 12 of positive and I found 88 of negative. Okay. Now, let's say you want to find, okay, which one of this model I should have used. And let's say for us, it's important to look at precision. What does precision mean? Precision means that if I make a prediction that a positive is going to happen, what percentage of time I'm correct on those positive? That means that out of those positive that I found, what percentage they were actually positive? So if precision is important, okay, which one of B and C would you use, for example? B, right? Because B has a precision of 100. This one has a precision of 10 over 12, right? Which is like 88%, something like that, right? The precision here is 88%, precision here 100. Because here you found 8, but all that 8, they were positive, so 100%. What if recall is important? Recall says that out of all the positive case, what percentage of those you found? Okay. If recall is important, which one would you pick? Out of all the positive cases that you had, what percentage did you find? That's recall. C, because you found 100%, right? Here you found 80%. So when you want to define which model is better, they always, in the real world scenario in companies, basically, the project manager, the lead, that basically some orders comes from the higher up. They say that, hey, we want to make this model. This is the bandwidth you have for precision. You shouldn't go below this. This is the bandwidth you have for recall. You shouldn't go below this. It's not like that you develop a model and you need to decide which one is good. There is some threshold defined in advance that you know your goal is that you can reach a model that has precision above 95%, reach a model that has recall above 96%. Okay. Based on that, you decide which model is Now, if you look at these three models, which model do you think is good? The best one, which one you pick? Like, let's say you are not given a precision or a recall.
A.
Why A?
I thought the first one is good.
A is correct. That model has learned to flip the order of the answer, right? Multiplied by negative is 100% accurate in most classes, right?
So keep me confused every time you answer.
What was that?
But
No,
you
so
did
think
that-
about it. I have a model that is exactly classify them, but in the printout, it's for some reason, maybe it's a bug in your code, maybe something, it just returns a negative of the answer. So if I have that, I just multiply it by negative and it's 100% correct. Correct?
Still we have a.
Yeah, what?
Still the model is not detected correct. Okay,
No.
we can tweak the model.
No, this model tells you that all the 10 that they were class positive, they tell you they are class negative. For the 90 that they were class negative, it tells you they are class positive. That means that it correctly separated them from each other. It's just a sign that it returns is wrong. Maybe there's a bug in some part of the code. There's a negative sign, you're making a mistake.
Isn't that the worst model then, like it's giving exactly the opposite answer?
No, that's the
Maybe
best model. If I have a model that is separating with negative, doesn't matter, it tells me this is 0, this is 1. If I know that, I'll just reverse it, like mirror it. That's 100% accurate. So that's the different scenario. I didn't say on data. Right? So this is a mirror scenario. Now, that question that you see over there, I actually asked this in the interview questions from big candidates. And I put them data set in front of them and say that pick the best model. Some of them, they will figure it out. Majority of them, they just drop it. They don't even. So the whole idea of this type of interview question is that you need to question. You shouldn't just look and say, oh, this doesn't make sense. You need to question, okay, what's the meaning of this? But also in the real world scenario, we always have these things like this happens. You have a model, all of a sudden your model, why my model does really bad? And you go debugging, and you see that somewhere, one of the engineers put the negative wrong. So all the code was actually correct. And you just reverse the negative, and you see that you have a perfect model, right? So now, get back to here. That's for precision and recall, okay? So now, there's a table here. Definitely review this table, okay? And not for this class, but for yourself as data scientist, you need to know these terms. The formula, it doesn't matter, but you need to know what's a type 2 error, what's a type 1 error. You need to know true positive rate, you need to know sensitivity, specificity, these type of things, right? Because you can easily go somewhere and someone tells you that, hey, give a name, like you're in the interview, someone says that, okay, I have a model with this sensitivity, and you can't just ask what is sensitivity or what was the formula for sensitivity, you know? It's expected for you as data scientists that you know this. So definitely review this table. Now, I said recall is, accuracy is bad, and recall and precision, it depends which one is given to you, which one is basically asked you to improve. What if none of those is basically, like no one told you that which one is better, recall or precision? Maybe both of them are expected to be high. Then you're going to use a technique, or basically a measure called F measure or F1 score. F1 score is a harmonic average between precision and recall. Simply is 2 times precision times recall plus, over precision plus recall. F1 score gives you something between 0 to 1. Closer to 1, the better. Higher, closer to 1 means both precision and recall are up. When it goes down, that means one of them was up, the other one was down. If it goes below 50%, that means that this model is like, just drop it. Don't continue. So now what we want to do, okay. So let's get back to here. So we wrote the remove those. So we know the cost function, right? So I'm going to write both the cost function, the log loss, and also the one that we had in the class. Let's say define cost function. So let's start with log loss. And log loss, I say, was summation of yi times log of the predicted value plus minus 1 minus yi times log of the actually. So we can get the predict. We already have the predict value. It's called discrete. Self dot predict that receive x and returns the sigmoid of that. So now loss becomes we have yi log that. So we want to write y minus dot log np right. That's the first part. It has a negative behind it. Actually, you can just write it as a positive and then multiply it by negative. So this one was 1 minus y dot np dot log 1 minus right. And cost is going to be 1 over x dash times shape 0 times negative of loss plus 1. So let's put this in the parentheses also so you can. This is the log loss, right? yi times log of the predicted value plus 1 minus y times log of 1 minus, right, for the class 0. And the reason we don't have yi anymore because we are doing it as a matrix form. X is a matrix form, y is a vector form. We don't need to write yi, xi. After you calculate, what's the size of the loss? What do you think is the dimension of the loss here? What's the dimension of pred? What's the dimension of x? So what's the dimension of pred? Pred is a predict. What's the dimension of your prediction? And by 1, right? So what's the dimension of loss? And by 1, you have m prediction, you get m loss, right? So you do dot sum after that vector, it's sum all those losses together as a negative, and you divide it by m basically, right, to normalize it. So that's one approach. Second approach, basically, we had. We need that theta transpose xi for this thread. So going to be x dot w. That's the theta transpose x. Now we want to calculate the cost. Cost is log of that term. So NP log of 1. So what's the dimension of thread here again? It's m by 1, right? Prediction. So that equation tells you log of 1 plus e to the power of this. But that's for one data. And now we are doing it for all data. So there's no summation, right? So can I write 1? Or should I treat 1? Should be identity matrix, right? So this becomes log of np dot 1s minus np dot exponential plus across. Right, that's the log part. Minus y dot thread. You dimension mismatch. This might be later thread dot y, but we will check it out. So, and then and put dot sum. So let's do one thing actually. Because this one is normalized, this one is not normalized. So for the first one also, let's just not normalize it. First. And then you will return first. So now the next thing we want is a deviation, which was another summation I from 1 to n xi sigmoid theta transpose xi minus yi. Right? That was the deviation for the logistic regression. So we find cost derivative. Well, that's going to give us the prediction value, which is that sigmoid value. Actually, no. I'm making one mistake. So predict, I forgot. Predict doesn't return sigmoid. I have been calling it predict as a sigmoid. So this one, it will this one requires the sigmoid, right? Sure. Yeah. So you need to call over this also. You need to call self dot sigmoid. Because predict will return us theta transpose x or x theta, right? And we need to pass it to a sigmoid to give the sigmoid values. So here also we need a sigmoid over there. So self dot sigmoid. Now the gradient is basically x dot sigmoid minus y, sigmoid or thread. Actually, let's call this better so we don't mix it. So this is a sigmoid value, it's not a prediction. Sigmoid minus y. Also, we can call this sigmoid. So this will be gradient, and then we just return gradient. Does this make sense? The gradient comes from this formula, right? X times sigmoid minus y. We don't have a summation because we are writing with this with the total data set. X dot sigmoid minus y. Only we need to write sigmoid minus y dot x because sigmoid minus y is m by 1. X is m by d. So it's going to be the other way around. This dot x. Okay. And what's the output of that? What's the dimension of grad? What do you expect with the dimension of gradient always?
And the dimension of theta.
Right, but what's that? How many columns you have? D, right? Always gradient, you learn theta. If you have D column, you learn D theta. So for gradient also you need to every time has D gradient.
This is sigmoid minus y. It's m by 1, right?
M by 1 minus m by 1.
It's m by 1.
Right.
What's this?
X is m by d. So probably we need to do some
X, and then you can
X transpose.
X, and then sigmoid minus y transpose.
Let's see. Let's we will get it. We're gonna get some error. We get the what's the dimension? But you're right. So if that's m by 1, then that's m by d. We cannot multiply it. So we'll get to that. Let's continue. So we have a cost function. We have a cost derivative, right? So what else do we need? We need a gradient function, right? So define gradient descent self the gradient descent is similar to what we had before. Basically, it's the same thing function, right? Create a vector that you can save the errors in it. You need the previous error, you need the current error, you need to update data, and then you need to basically check convergence, right? So errors goes here, then I will say that last error, I will assign it to be float infinite. Then I will write for I in EQ them. Range of self dot max iteration. So in each iteration, what we want to do is that we want to update W, self dot W equal self dot W minus self dot learning rate times self dot cost derivative over same x and y. After you update the W, what do? You test it, how much error this W is giving me, right? So current error basically becomes self dot cost function over X and Y. Now we have updated the new error. Now we check the difference between the previous error and the current error. Then we set the last to be current. Then we check if difference is less than self dot epsilon. Then we will print the model stops and we break the loop. After that, we can basically do self dot plots cost and pass the errors to it. So that basically perform a gradient descent, and after that it will plot the cost function, cost basically iteration plot. Now we want to write the function now because we talked about the evaluation. How do you say how good was my model? So we need to write a function for evaluation. Questions?
Or errors, any
Oh,
kinds
yeah.
of errors.
Oh, nice. Yeah. What's the errors? How can yeah, thanks. Okay. Now we want to create a function called evaluate. That this function, let's say it gets y and y hat. Y is the actual value, y hat is what we predicted, right? So, and we want this function to return precision, recall, FS score. Okay, so let's start with, so we know precision is that out of all the positive we found, how many of them were actually positive? Okay. So one way, this is one approach, again, you can code this however you want. One way is that, so I know y is a vector of 1 and 0. Y hat also is a vector of 1 and 0, right? So one thing I can do is that I can define y to be well, y equal 1. Anyone knows what will happen over there if I say y equal 1? What's that? It converted to a Boolean. Any place that vector of y has a value of 1, it becomes true, the rest become false, right? So I'm converting a y to a true false vector. Do the same thing for y hat. And we do it with respect to class y hat. With respect to class 1, because that's a class of importance for us, right? So now I have two vectors, both true, false. And they both are true wherever class is 1, right? The definition of precision was that out of all the points that I predicted as true, how many of those are actually true also in the class, in the y, basically, right? So I can say precision equal y and y hat. Two vectors true, false. If you say y, this add, it will return you true places that they are actually both true, right? So divided by y hat dot sum. That also becomes how many we predicted to be true. We call same thing y and y hat. Out of all the points that we basically are predicting are common across these two, right? Yeah. We found. Was that? It's true for some also works. We do on a vector true false dot sum, it counts the number of truths in.
Vector, left one.
Oh, you mean on, right, sorry. Dot sum. So this time we divide it by y dot sum. Out of all the points that you have correctly classified, okay, this tells you the number of points that you correctly classified divided by how many total you have, right? This is divided by how many you actually classified as. So precision versus recall. Now, FS score, this becomes 2 times precision times recall over precision plus recall, right? And you want to return FS score, precision, recall. Now define fit function basically. We are going to basically put everything in the order that we want. So we already have this self dot post in it, which loads the data, adds a column 1 to it. So we don't need to call that anymore. So we will here basically define self dot w. We can see NP ones, and it's going to be self dot train x dot shape 1 equal NP dot loads. So then we are going to call to self dot median descent. We pass self dot train x self dot train y. That will update the W for us. Then we can evaluate it. We can say that what was the F1 score, and measures that I have is we can say that self dot evaluate first over the train that requires train y and y hat. So we don't have y hat, so let's create y hat. Y hat is the predicted value, right? So self dot sigmoid self dot predict now the sigmoid here is not returning so the evaluate expect that your predicted value to be 0, 1, right? Sigmoid gives you a value between 0 to 1. It doesn't give you binary, right? You need to define that threshold, remember? So for now, what you could do is NP around and pass y hat to it. That defines a threshold of 0.5 and converts it to a binary, right? But for later, you need to have a function technically. You create a function that has a threshold as an input. Maybe user wants to change that 0.5 to 0.8, right? So you need to basically have a function that does that. And you're going to print the F1 score and so just run this. And then we need a file pass. And the file pass is myself. I need to miss also. Yeah. First part was that you initiate the data set and then wait that feed. Let's see what error we get. Number that ones. Similar feed. Here, number that ones.
Second approach.
That's for the
Where there is
Cost function.
Why?
cost function.
We don't want.
I don't see anyone.
Cost
Which wait, is the one? Oh, here. Okay, right. Okay. This is the other. So we're missing. See what's happening in the cost? There's a negative, right? That should be the other way around. Everything is negative. It should be positive going down. So there's a negative sign. The cost
Minus cost function.
Cost function here. So we are returning this one, right? That this one is coming up, right? The second one. So we are doing summation of, do a prediction, get the print value. Let's call this self.thread.
Minus log.
And that is log of that minus that term. Is it the formula of minus log or log?
Minus log. First term was minus.
We had so it was positive. Log of that term was plus positive cost. So this so the gradient. If we use the first one, what do we get? It says that we need to have a negative behind this one, but not based on the formula that we have. The formula is log of 1 plus e to the power of minus yi theta transpose xi. NP log ones of 1 plus e to the power of. Yes, so that should be correct. I'm not sure why this is giving it reverse plot. Let's keep that one there. So let's see what's the second error I have. Evaluate is missing y hat. Y hat. Let me pass y hat out here. Y hat. It says the F1 square was this, the precision was this, and the recall was this. So we can just also round it, basically, NP that round those values maybe is better. So let's return, evaluate. Let's go around this one. Now, there are a couple of functions that I give over there. One is that scatter plot. So you can say R dot scatter. dimension mismatch. The other one. We need to update the plotting. Need to update the plot function. I thought that occurred. But so that's logistic regression technique. Let me review this the cost function, then I will just send an update on it that to see why, because we shouldn't multiply this by negative based on the formula. There is something else somewhere, something I'm making a mistake. And I will update the plot functions. So the reason for those plot functions, example of what are those plot functions. So those plot function technique are going to return you this. One of them is going to return you a 3D plot. You have two features, x1, x2, where the values that they are providing, what's the probability of point being class 1? Higher, the points belongs to class 1, lower, the points belongs to class 0. Now, then there is another plot function which it would create a decision boundary in the 3D format. There's also a decision boundary in the 2D format. Now, your goal is that basically lab that you would receive is that the question will be, there are some outliers. You need to remove and rerun the model. And when you run the model, you will see the lines start shifting, right? And there are some questions that you need to answer. One other thing is that I think one part of your lab also talks about there's a gradient part that you need to check the impact of gradient on the movement of the underlying the decision boundary. So the function is given. I need to just review that why as right now just the decision mismatch is happening. The dimension mismatch is happening. I will fix the plotting function, and you have this question. The lab would be you need to update it probably. I don't know. I think you need to do regularization, add regularization time to logistic regression, and then answer a couple of questions. It's clear. Yeah.
For the cost,
Yeah.
why do you get minus loss?
That's what I'm trying to go. I need to check it.
I think you get it in the formula before, the minus loss. It was minus the first time.
No, so I use right now. I use the first one. That's why I'm getting correct.
Yeah, the second one, I think that formula is when you get the minus loss.
The minus loss should be positive.
Yeah, I know, but I think you're applying minus twice.
So we had. So this was the. You had J of you had MW, which was this negative of log.
Sorry, I wrote it.
So this one should be this one should return you a positive. This one will become a negative. Not quite sure why that. Anyway, let me review this. Maybe you guys also figure it out yourself. There's somewhere I'm sure there's one minus that we're making mistake. And this is one of those scenarios I told you that your model is correct, but you get one minus that it flips the answers. Okay, so I leave this one here. For next class, first I think you're going to you already have the new homeworks that you receive. So you will have I will post a lab, and it's going to be some in-class problem, which I definitely recommend to before exam. Whatever in-class problem comes, to just pay attention to. Now, one other thing is that so for next class, at least for the next two classes, try to not